Thanks for that intro, Julia. I'm also very excited for this series. Thank you all for attending. Just a brief overview. So the structure today is we're going to have about a 30-minute presentation by Dr. Loftis. Then there's a few prepared questions that I have, and then we will spend the remaining time from audience questions. So as Julia mentioned, please make sure to put your questions in the Q&A, and I will be able to field those for our speaker. So without further ado, I will turn it over to our first speaker, Dr. Derek Loftis, who is the Research Assistant Professor in the Center for Coastal Resources Management at the Virginia Institute for Marine Science. So Derek, over to you.
Thank you for the invitation to speak, Kristin. Thank you for the introduction, Julia. So the title of my talk is focusing on validating operational flood forecast models using sensors and citizen science. And as a research assistant professor at the Center for Coastal Resources Management, a lot of my work really involves me providing information to the Commonwealth of Virginia's state-funded flood center called the Commonwealth Center for Recurrent Flooding Resiliency. And in the example here shown in the background, my title slide is some examples of some urban flooding in the city of Norfolk, Virginia, on the south end of Chesapeake Bay. This type of event happens about every year or so just due to tidal flooding. This particular example is just exacerbated by wind, creating a seiche in Chesapeake Bay as winds blow from the north towards the south end of the bay. And so some of the challenges that we really see there is that we've got a lot of interest in terms of trying to validate the accuracy of very high resolution flood forecast models like those that I developed at the Virginia Institute of Marine Science, along with colleagues at other partnering institutions throughout Virginia. So the outline of my talk kind of more or less takes a format of a thank you, in the sense that I'll be focusing on a couple of different projects related to citizen science efforts to help us validate our models, but also sensor projects using IoT or Internet of Things style water level sensors that help provide additional insights beyond those that are funded by the federal government, like sensors that NOAA and USGS manage. So it'll kind of operate as a thank you to volunteers, teachers, what we call Tide captains, which are essentially individuals that help train others how to help collect meaningful water level data using their mobile phones. And then we'll also talk about how we organize these types of large citizen science efforts and how we organize with local communities to help install sensors that will help us validate the accuracy of these types of flood forecast models that we're developing. Also kind of focus and highlight student projects and school groups that have been involved with these projects, and ultimately the modeling research that myself and others are conducting in a collaborative nature in coastal Virginia, along with a mobile application called Sea Level Rise. It's really available on iOS and Android platforms that we've been using to help validate our models, and then go into further detail on exactly how we validate these types of models on a broader scale. Now, one of the challenges that we really encounter with this is that there's a lot of different projections out there in terms of what we can expect to see in terms of relative eustatic sea level rise. When we're looking at different types of publications, Tal Ezer and Larry Atkinson in 2015 at Old Dominion University published a paper that directly focused on the number of hours per year that the historic area of The Hague and Norfolk is flooded. And one of the real challenges that we kind of encounter with this is that from year to year, based on the Sewell's Point water level sensors that's been in place since 1930, near the Norfolk Naval Base has been tracking specifically how frequently the water levels eclipse 4 feet above mean low or low water. And so, of course, you got historic observations in the dark colors, but then, of course, projections between 4 and 8 millimeters per year. And this is not, of course, just global sea level rise, but also compounded with land subsidence in lower Chesapeake Bay that kind of puts this in a range that's projected to be between 4 and 8 millimeters per year. And the real challenge with this is, of course, now you've got a lot of government agencies that have their own projections, and then the Commonwealth of Virginia with their own specific projections that they're planning for looking forward. And so if you look at Billy Sweets and his team's report from NOAA in 2017, you've got a series of ranges to look at in terms of the intermediate high being specifically the one that the Commonwealth of Virginia is using as their particular scenario for planning that was called out in a recent executive order by Governor Northam in the Commonwealth of Virginia, but then also the U.S. Army Corps of Engineers and, of course, other places have their own specific projections. And as you might would imagine, this becomes problematic for local and community planners as they start to look into broader contexts of what you can expect to see merely from tidal flooding events in the future. And then of course, on top of that, when you look at past historic storm events like 2011 Hurricane Irene or 2003 Hurricane Isabel as the historic storms of note for Virginia's coastline, this just continues to stack up on top of those projections looking forward. And so at the Virginia Institute of Marine Science, where I work, we've also produced what we call sea level report cards that give us additional insights into specifically what we've seen based on long-term and short-term trends at individual locations, what you might would expect to see in the future based on the different sources of contributing to sea level rise in different places. Now, of course, we provide long-term and short-term forecasts. In this case, the near term is usually focused on hydrodynamic modeling that's driven by data from the National Oceanic and Atmospheric Administration's National Ocean Service, but also data from the National Weather Service for winds and pressure fields. And this information provides us a lot of data that we need to validate in terms of our relative models. So we have an operational forecast model, and basically what you're seeing here in the background is water level data from Sewell's Point and Norfolk. And my focus for my research is validating flood models with sensors and citizen science. And so each of these little blue dots there represent or a mobile application that was released in 2014. We've been using for about the past 6 years or so. This will be coming up on its 7th year since it's been deployed. We've been using this mobile application called Sea Level Rise, and I apologize, this animation's a little jumpy with the bandwidth, but basically I've highlighted this line based on data collected from Sewell's Point to help highlight when we've had volunteers go out and use their mobile phones to help validate the accuracy of flood observations from sensors and forecasts from our models. So when that line starts to change to a red color, that's basically when these streets and other places in downtown Norfolk and Virginia Beach and southeastern Virginia become flooded. And of course, those are the particular problems that we've got volunteers that essentially will go out there and measure with their mobile phones, specifically what the extents of flooding happen to be in those localities. They do this by using the Sea Level Rise mobile app that's freely available on iOS and Android platforms, and they'll drop GPS digital breadcrumb by pressing a button regularly on their mobile device as they walk along the wet-dry interface during high tides. But of course, after storm surge events, there's also a notes field within the app that they can indicate that maybe you should ignore this timestamps that are collected with these GPS breadcrumbs and instead focus on the fact that they collected data, after a major hurricane by following debris lines when it is safe to do so. So we've got a lot of protocols for our volunteers to make sure that they're not putting themselves in harm's way to collect data. But in this case, it allows modelers like myself to be able to collect these data in a meaningful way. So this is kind of a way to show you the last 5 or 6 years of what water level flooding in the city of Norfolk and in Virginia Beach has looked like. So as we kind of explore these, we developed a product that ultimately is pushed out twice daily at noon and midnight. Called Tidewatch. And this particular map allows people to actually view tidal flooding and storm surge related flooding throughout coastal Virginia. And so as we map king tides, and most of our tidal mapping efforts are focused on the fall, this effort that we call Catch the King essentially is something that you may have heard of through Esri's blog back in 2017, and they published updates in 2018 and 2019 for an article that Don Wright, a relatively well-known oceanographer in our field, the chief science officer for Esri, wrote a blog focused specifically on our inaugural year when we started this initiative called Catch the King and focused on getting hundreds of volunteers to help us map the relative flood extent of the highest astronomical tide of the year in the Commonwealth of Virginia. And every year since then, we've continued to expand our efforts. I was also featured on Science Friday about a year and a half ago to talk with Ira Flato specifically on how folks can use their mobile devices to look and view our flood maps in real time, and also then take the information from those forecasts. And the core ask of Catch the King is basically posting these maps in advance to say, hey, this is where our model thinks it's going to flood tomorrow. Can you please go check? And in this case, this 36-hour window allows individuals to go back and evaluate whether or not our model was accurate based on places it predicted to flood from tidal flooding. And so we were also featured on CBS This Morning in this past year, along with the Weather Channel about a year ago or so now. And so this year, we're already really looking forward to this being our 4th year of collecting data through Catch the King. And this has really been a very valuable resource for us to help validate the accuracy of the flood forecast models that I helped develop as a physical scientist at the Virginia Institute of Marine Science. So a lot of people tended to be skeptical of citizen science initially. In this case, it usually involves people emailing me photographs back in 2013 and 2014 when I completed my doctorate, focusing on flood forecasting with Hurricane Sandy in New York City. And so initially, we quickly were able to pull a lot of data and were able to have lots of people share even information from like ATM cameras in New York City and public traffic cams. All kinds of information were coming in and trying to find unique ways that we could help validate flooding using video and photographs. But one of the real challenges that's involved is that usually GPS is telling us exactly where people are focused. And nowadays with mobile devices, it'll even tell you what direction people are focusing or standing in terms of relative degrees differentiated from due north. We now have an idea of exactly where photographs that are being collected with these apps are being taken. And so over the last 4 years, the real value for me is that we were able to validate the accuracy of flood forecasts. So as we collect all of these individual data points, I post them into a map for data transparency. And so we've got red dots representing sensors. And so the proliferation of these sensors over time also exists, but also these blue dots where we've actually had citizen scientists go out there and help us collect data. And over the last 4 years, we've been able to map a large portion of Virginia's tidal zones throughout the eastern shore, but of course also throughout the main peninsulas that represent the western bank of the Chesapeake Bay. And so the way that we kind of organize this is I release annually a tidal flooding calendar based on data from NOAA from different sensors throughout the Commonwealth of Virginia, along with our Tidewatch forecasts through a program that we manage at the Virginia Institute of Marine Science that helps us provide some insights into when the full and new moons are, and specifically when we anticipate king tides to take place based on harmonic extraction. In this case, we just basically look at water level sensor data and the overall implications of the moon and the sun's relative impacts. And as those tidal fluxes bend around the landform, it gives us a little bit more information on exactly where we expect to see those tidal peaks and troughs annually. And so we already know when the highest astronomical tide of this year will be in October and November. And so we've got training events set up in October, and our Catch the King event will take place on Saturday, November 6th in the Commonwealth of Virginia. And so knowing this months in advance, this gives us a target for training volunteers to help us collect GPS data breadcrumbs that we can then use to convert to digital contours and compare with the flood extents predicted by our models. So in 2020, for example, the last year that we did this, we'll be doing this again, as I noted, on November 6th in 2021. So we're training virtually and in person new volunteers to help assist with this. Naturally, with the pandemic last year, it's one of the smallest years we've ever had for Catch the King, but we still were able to collect on October 18th, the highest astronomical tide of 2020, nearly 27,700 high water marks from 184 individual volunteers. Specifically on Sunday, October 18th, during a 6-hour period throughout the tidal zones of Virginia, North Carolina, and Maryland. But also throughout the rest of the year, we had 42 avid volunteers that will help volunteer their time to collect other types of flood events. For example, like Hurricane Isaias that came through last year in 2020. We had volunteers to help collect data after that, even though it wasn't, thankfully, a significant flood event. We still got a lot of validation for our model in different places based on wind directions emanating from different distances and from different directions that help us validate our model, even for the small storms that will come through. Now, of course, to make a particular event like Catch the King work, I provide a lot of different types of graphics to share our data back with the public based on data that they'll collect. And so each year, Catch the King is a community-sponsored event. And so throughout the course of releasing data, I'll usually produce some form of story map through Esri's ArcGIS online platform. And ultimately our media partners through the WHRO Public Media, which is our local NPR and PBS affiliate in Norfolk and in Williamsburg, Virginia, helps with that in a large part, but also the Virginian Pilot and Daily Press in terms of print and digital media help get the word out. And of course, the state-funded flood center in Virginia called the Commonwealth Center for Recurrent Flooding Resiliency help us get the word out. So in this case, for example, in 2017, our inaugural year in doing this, we got nearly 10,000 individual engagements from volunteers that led to over 900 volunteers actually directly collecting data in 2017 for Catch the King. The reason why I mention this mostly is because this garnered a Guinness World Record for us as the largest environmental survey on the planet, and we collected 59,718 high water marks in a 6-hour period on November 5th, 2017. Now, of course, since then, we've continued to expand our reach. And so WHRO Public Media has really helped us engage with student volunteers from middle school and high school ages. And we've kind of integrated these within the standards of learning in public schools. So we've gotten middle schoolers and high schoolers involved through social media engagement on Facebook. We've got a group of over 1,000 participants that we regularly engage with to help us kind of point out when flooding is anticipated to happen, but also to inform people how to use the Sea Level Rise app to collect these data. But also we focus on these standards of learnings, or SOL, in this case to focus on physics and mathematics concepts like trigonometry, water chemistry, and relative water quality, but also the mathematics of waves in general that involve the tides. There's also a couple of student projects I've worked on with high schoolers and of course college students. For example, this is a student in 2019 in high school that collected data and helped install these physical staff gauges in different places with QR codes that were attached to the tops of these gauges. And in this case, people could scan these and upload these to web maps that would actually tell us, not just using their mobile device, what digital contours would look like based on maximum flood extents, but also depths. Since most people are probably familiar with the fact that your phone's pretty good at identifying loosely where you are in terms of the XY plane, the Z is usually a little bit less accurate. In most cases, the best you can hope for in terms of vertical elevation estimation from your phone is maybe what floor of a building you might be on. So it's usually plus or minus about 6 feet on the vertical scale. So as a result, these staff gauges help, but also, of course, we've built some fun, animations and, frames that you can put on Instagram and Facebook for your social media engagement to tell people, hey, I'm involved in this thing. And that involves people engaging on a higher level. For example, last year, even during the pandemic in 2020, the Girl Scout Council of Colonial Coast in Southeastern Virginia collected 4,630 high water marks among 24 Girl Scouts that helped collect data. But also master naturalists and master gardeners were a big help in this effort, as 47 of their mappers collect 5,600 or 5,971 high water marks in the more rural areas of coastal Virginia, in the Middle Peninsula and Northern Neck, between the York River and Rappahannock and the Rappahannock and Potomac rivers, respectively. And so as a result, we kind of share these data publicly. A lot of these individuals collect data that help us validate not only, of course, where the GPS locations these images are, but also the efficacy of the app is useful because now it allows us to know directly what direction these individuals are facing. And so as we translate these into our model's three-dimensional representations of water levels using Google Earth and Google Street View, we've now been able to actually overlap what our hydrodynamic models elevations look like in terms of flat static layers of flood elevations, and actually being able to identify exactly what those look like from a three-dimensional perspective as well. Now, a lot of the data that myself as a flood forecast modeler happen to share is through a website called adaptva.org. And this was one of the facets that helped garner a special achievement in GIS award back in 2019 from Esri at their Esri user conference. And we released these data through water levels, but also water level viewers. So you'll, of course, see these through data that are shared through water level gauges, but also our Tidewatch viewer at the Virginia Institute of Marine Science. By clicking on these links, it will basically take you to water level sensors where there might be forecast data that are basically collected from IoT water level sensors. For example, this is one within the StormSense project that I manage, which is an Internet of Things water level sensor project that is managed by the city of Newport News. For this particular gauge, this is one of 10 water level sensors throughout the city. And so this is a data set that we manage at the Virginia Institute of Marine Science that helps us collect additional data beyond the federal sensors funded by NOAA and USGS. So we, of course, provide forecasts for those sensors and share those with our local National Weather Service branch in Wakefield, Virginia. And so these root mean squared error comparisons, for example, with a tidal flooding event last year during the king tide, helps us validate in terms of the predictions shown in this magenta line compared with the observations that are shown with some of the variability, for example, for the Chesapeake Bay Bridge Tunnel here with the NOAA sensor. And one of the beauties behind this particular project of StormSense is that we're integrating data not just from NOAA's sensors, but of course those from localities like Newport News, the city of Virginia Beach, along with those from the U.S. Geological Survey. So in this case, it integrates data from multiple platforms and multiple sources without having to go to 3 or 4 different websites to be able to see these, but also it validates the model in real time as these water level sensor observations are taking place. So it allows us some direct focus on exactly what is happening on the ground. To do this, we basically ingest 2.4 gigabytes of data, looking over a 36-hour forecast period at 3-kilometer spatial resolution and 1-hour temporal resolution to basically forecast flooding throughout Virginia's coastal plain up to 36 hours in advance using our Tidewatch forecast map shared through the Adapt Virginia portal. And it does this throughout Virginia's tidewater region at approximately 3-foot resolution on the spatial scale. So while, of course, the atmospheric products are at 3-kilometer scale, we are using LiDAR data that's directly integrated into these interactive web maps at 3-meter spatial scale, or 3-foot spatial scale, or 1 meter spatial scale to do this. And I say 2 different resolutions because in some areas we don't have a 3-meter resolution, and in some areas we don't have 1 meter resolution. So for example, in Virginia's Eastern Shore, we have coarser resolution LiDAR data than we do in other places. So it varies. For example, in most of our local communities that are urban environments, we have 1 meter resolution predictions. In other areas, they scale to a coarser resolution at 3 meter. And it does this twice daily at noon and midnight, updating our flood forecasts. So in reality, in terms of scaling metrics, our 36-hour simulations take 1.25 real hours using 72 CPUs in our high-performance computing platforms, the College of William and Mary, where we run our schism model as an operational forecast model. So it directly ingests these data that are being provided by the National Weather Service regularly. One of our most significant recent storms was Hurricane Dorian in 2019. We were able to directly compare and actually identify and isolate some of the impacts of these storms for each of these individual blue raindrops. These are water level sensors that we have established in North Carolina and coastal Virginia that actually experienced some relative increase of flooding in some of these spaces. And so as we're able to go back and evaluate what the forecast plots for these dashed red lines look like versus what was actually observed after the fact, we then go back and evaluate. Because one of the challenges that modelers like myself have when we go through and evaluate our models is that we don't necessarily always know whether or not we're calculating these things correctly. And so a lot of people will ask, well, why are you installing all these new water level sensors? The federal government will eventually get around to it. In this case, the reason why is this example here at the bottom. We had just previously installed a water level sensor in the southern watershed of Virginia Beach, and we previously assumed that our model was doing a great job. And in this case, we realized that there were some inadequacies in the way that we had coastal waterways digitally resolved for some very narrow tidal creeks that needed to be properly carved out, where we've got issues with virtual dams that are being formed from aerial LiDAR survey data. And so as that happens, that allows us to collect additional information to help validate our model. And so we can go back and fix those areas before a more significant storm event comes through. So the way that we do this is running a large-scale hydrodynamic model, and this covers the entire Atlantic and Gulf Coast. And then we ingest these atmospheric data along with storm surge information driven from pressure fields and wind fields. And then we ingest information for building elevations for buildings in the coastal zone and factor in for long-term sea level rise and land subsidence when we're looking at longer-term forecasts beyond just the next 36 hours. And then we share these information using an embedded Web 3D application through the Esri's web apps. In this case, it will basically allow us to highlight individual buildings that might be impacted. And so we published some of these results in the fall 2018 article of ArcUser, along with one of my collaborators, Jeff Kaler at Esri's dev team. And this allowed us to compare what these water level data look like with other models, like the National Water Model. And so on the ground, this is what it looks like in the city of Norfolk, bordering the edge of Virginia Beach. And so you saw this on the title slide as well, that you get this kind of flooding for this example around the time of Hurricane Matthew back in 2016. But then, of course, if you highlight these data, this is essentially what it looks like when you're looking at all these individual stream reaches and the relative discharge from each of these areas. And so you see this big pulse come down the Elizabeth River, connecting Suffolk, Portsmouth, and the city of Norfolk as it discharges out to Chesapeake Bay due to the heavy rainfall during Hurricane Matthew. So the way that this works is we run our large-scale hydrodynamic model, which functions as a street-level model. It incorporates flooding from tides, storm surge, and rainfall, but also drainage from soil percolation, groundwater infiltration, and stormwater drainage. And so you can look at this from an inland perspective, but also coastal areas. So I'm going to kind of zoom in on this inland area since the main impacts were rainfall and compound flooding from Hurricane Matthew's relatively significant storm surge. In some cases, it rose the water level by 2.5 to 3 feet, which normally you wouldn't consider that significant. But when you compound that with 14 to 16 inches of rainfall in a 72-hour period, it became problematic for areas that are not even zoned within the floodplain zone AE, which are what's represented by these individual blue dots on this map in the city of Virginia Beach near Lake Windsor, which is an inland area that's multiple miles inland. And of course, during Hurricane Matthew, our hydrodynamic model very quickly identified some areas that immediately started to become flooded during Hurricane Matthew. And naturally, this former creek bed that was paved over to develop this neighborhood called Windsor Woods in the city of Virginia Beach immediately became inundated when the amount of capacity for overland storage for water immediately was filled within the first 3 hours of Hurricane Matthew's rainfall. And so I'll be zooming into this from the 3D web visual here in just a moment. But as you can see, far more than just the individual points that are represented as those that are within the floodplain are impacted due to the relative wind direction of the storm, but also relative drainage capacity. And so on October 9th in 2016, you can actually see the water levels slowly rising over time as this takes place. We compare this with the discharge of water level data that was anticipated and interpolated from flow gauges the U.S. Geological Survey has installed in this portion of the edges of Thalia Creek in the city of Virginia Beach. But also you can see the storm drainage that's taking place. And so slowly the water makes its way to the edges of these cul-de-sacs and is drained out over time. And so we use this to help validate in terms of the amount of actual temporal flooding that takes place. Is the period of the flooding correct, but also the relative discharging velocity. We found that this compared actually reasonably well in terms of cubic feet per second between what was actually observed versus predicted for each of these individual examples during Hurricane Matthew in 2016. Even for these relatively small discharges, we got them relatively accurate. From a geospatial perspective, this is an example looking at a king tide in 2018 and comparing with Hurricane Florence relatively later on. Unfortunately, North Carolina took most of the brunt of this impact. So the actual king tide in September ended up being a slightly higher water level, but this is where volunteers help drop these GPS breadcrumbs using the sea level rise app and how this compared with a forecast from our hydrodynamic model that was released a day previously. It doesn't perfectly match the floods, Jake, because some of this space is private property in people's backyards that we can't actually send people back there to map. But in this case, we encourage our volunteers to stay within public spaces, and in this case, use either their iPhone, iPads, or a variety of different Android devices to collect these digital breadcrumbs, and we ingest them into GPS and GIS platforms to convert these to contours, and then compare these with the relatively pixelated 5-meter resolution digital elevation models of our hydrodynamic models, and compare the overall distance deviation between the predicted and observed values to give us this statistic that we call mean horizontal distance deviation. It has a lot of meaning when the ground is relatively flat in certain areas, but of course, naturally, the value of the statistic deteriorates quite a bit if you have very steep slopes. And so over the course of looking at each of the individual hours, we've published these results back in this example of 2016 during Hurricane Matthew and Hurricane Hermine, and data from 2015 during a couple of storms like Hurricane Joaquin. And basically the data transparency is really the focus here. We allow volunteers to see where they've collected data during these events. They can also access water level sensor predictions on these maps. And so as we share these data initially before a storm event, none of these blue lines are here. They start to pop up as individuals collect and share data through the Sea Level Rise app. And naturally these relative size of these points become smaller and smaller as you zoom in to eventually see the timestamps of individuals showing where the flooding extents took place. And naturally, as you see the maximum tidal extent takes place over time, individuals can see where their individual GPS data points pop up and whether or not our model predicted flooding in some of these spaces. There's also, of course, measuring tools so people can compare the water level data that they measured. So student projects, of course, then have enabled them to look at and say, okay, it varied by plus or minus 20 feet or so for some of these individual values. And so when you're looking at the relative accuracy of data collected through LiDAR, this is actually pretty decent. So this allows people to verify how accurate our models were, not just geospatially for maximum flood extent, but also temporally. So of course, these values change with our model's hourly outputs from 8 to 9 a.m. to 9 to 10 a.m. at different places throughout the city of Norfolk. And these examples here from last year's King Tide events, but also parts of the city of Virginia Beach, like some of these that are shown here. And that deviation changes from hour to hour. So as we start to provide these aggregate statistics of whether or not our model actually matched these spaces, it gives us some GIS methods for comparing relative shapes of the flooding, but also the relative volume estimates. These are things that are important because one of the key values of Catch the King and validating these models this way is it helps us validate for relative hydro correction. What this means is essentially physics-based models like hydrodynamic models really rely heavily on whether or not you actually represent the total tidal volume and storm surge volume of water that is making its way to inundate the land in certain spaces. In some cases, bridges like the example here that are not fully carved out of the digital elevation model kind of form a digital dam that doesn't actually exist in reality. And so in this case, you can see a culvert that regularly, even with the imagery, you can see this area of the city of Norfolk should be regularly inundated. But naturally, this culvert was not fully burned into our digital elevation model, which represents the elevation assumptions of our hydrodynamic physics-based model. And so basically by calculating using GIS, well, what is the distance between each of the blue points that our volunteers collected with the maximum flood extent predicted by our model, you'll see some of these are hundreds of feet away from the nearest flood points. And so I focus on those and then ultimately go back and fix or correct the digital elevation model that our information uses as an assumption. In this case, you can see it starts to fix the overall volume estimations of our model. And we learned this pretty early on. This is an example from the New York City, specifically in Brooklyn, where we've gone through the process of looking at my digital elevation models from my hydrodynamic forecast of Hurricane Sandy in New York City, and found that it was critically important to fix this area of like I-278 in Brooklyn, where some of these neighborhoods were actually flooded, but initially our first forecasts missed these areas, which resulted in overprediction in some areas and underprediction in other spots directly adjacent to this neighborhood. And so as we try to improve and perfect our approaches here, we found that in 2020, our flood forecast models were accurate using 26 water level sensors from the StormSense program, along with those from NOAA and USGS. On the vertical scale, this was accurate to plus or minus 4.24 centimeters. And on the horizontal scale, this was accurate to 21.1 feet from the 27,700 high water marks we collected. Additionally, we also had volunteers that helped us collect water quality data, and they took those samples back to the lab with some of our partners at Old Dominion University. And in this case, in Norfolk, individuals collected data to measure tidal flood extent contaminations. Of course, when you have these major flood events, like this example you see here on the right-hand side, it's flooding past fences into people's backyards and other spaces. And this carries a lot of nutrients back to the river that ultimately overloads those rivers with high levels of nitrogen and phosphorus. Mostly because in the fall tidal flooding season, this is usually when people are fertilizing their lawns in preparation for the winter. And as a result, a lot of those chemicals make their way back to the waterways, heavily spiking those values, leading to harmful algal blooms that normally occur in the late summer to now extending them well into October and November in some of the tidal tributaries of Chesapeake Bay. We also effectively crowdsourced hydro correction, so our model gets better and better by even spending time just comparing using this very public form of tidal calibration through the highest astronomical tide of the year. So our volunteers with Catch the King assist with that. And also many of our volunteers assist us with private property access. So we don't just validate our data in public parks and right-of-way access areas, but also those that allow us additional insights into what is happening in places that we normally wouldn't have gained access to otherwise. And this year in 2020, the highest astronomical tide of the year that we'll be focusing on takes place in October and November, with our official Catch the King event taking place on November 6th in 2021 in the morning in Virginia. Thank you all for your attention and for the opportunity to speak. And thank you to all the individuals that are involved in Catch the King and StormSense's projects that helped allow me to garner all of these data to share with you today.
Thank you so much. That was a great presentation. That's really fascinating work. I'm going to jump right in. We have a lot of great questions that are coming through. I have a few pre-prepared, which I'm going to do a consolidated list of so we can get to these audience questions. But to start, do you like there are any critical aspects of urban flood resilience that currently merit more research attention, and or kind of as a combo question, do you feel that there are any calls to action you would like to highlight for our research policy and or practitioner community?
Well, certainly. I know one of the challenges that we kind of experienced early on is, naturally it's called nuisance flooding or tidal flooding for these events that are happening pretty regularly during these king tides. And of course, most people's experience with them early on is kind of the inconvenience of having to reroute their early morning commutes. And so one of the things that we kind of started to focus on, and there's a center in Virginia, it's called RISE, and it's an Urban Flooding Resiliency Initiative. It was initially started by the city of Norfolk through some funding that they provided through the Housing and Urban Development grant that they received. And in this case, they focused on traffic rerouting, mostly because there are issues with Waze, and Google Maps have this habit of directing people directly into tidal floodwaters because there's no cars on those streets. And there might be heavy traffic on the streets that are further inland because people are trying to avoid the tidal flooding that are locals and know these areas. In coastal Virginia, especially in Hampton Roads, they're really no stranger to tidal flooding, but also this is a large hub for large military populations that are new to the area that don't know the relative challenges involved with tidal flooding in areas that have a high water table and a relatively low elevation. And so, of course, the unfortunate rude welcoming for some of these individuals as they regularly move with the militaries, they're immediately greeted to moving to Norfolk and Virginia Beach and in parts of Hampton that flood frequently by being directed by these automated route guidance systems into tidal floodwaters because there's no traffic on those streets. And unfortunately, those systems are designed to direct you to streets where there's not a lot of congestion from traffic. And unfortunately, a lot of these newcomers are not familiar with the fact that the reason why there's no traffic is because it's under 2 to 3 feet of water. And so oftentimes individuals move to the area and then lose their car within probably 3 months or so of moving to this space. And so that's one issue that has been directly addressed and are continuing to kind of spawn some interesting concepts related to urban traffic sensors. Along with automated route guidance issues related to adding in Google Waze or Google and Waze's apps for like flooding instead of just indications that the street is blocked or closed. Now there is a flood icon in both of those apps. We've been ingesting those data to help advise where road raising projects need to take place through the Hampton Roads Planning District Commission.
Wow, yeah, that's awesome. Another question is, do you have any opportunities to collaborate or other opportunities in general you'd like to share with the audience today? For example, are you seeking any collaborators, student funding partners, and or are you open to people reaching out to you after this presentation?
Oh, absolutely. Always. We're eager to collaborate with anyone that's interested in being involved either with our citizen science work that I focused most of this presentation on, mostly due to its collaborative nature and interdisciplinary approaches for citizen science and social science. But also, of course, most of my work is in the physical sciences. So most of the research I've been involved in most recently is new types of passive water level sensors. Most of those in StormSense in our programs are non-contact active water level sensors using radar and sonar and ultrasonic frequency specifically for sonar for water level sensors. But we've started using AI and edge detection, basically web cameras in 4K resolution to help us detect water levels. And so this has, of course, given us visually what the flooding looks like in certain areas. But also, anyone that's got any interest in helping map flooding in their local communities, collaborative papers and research efforts are always an interest for us in terms of prospective students or potential collaborators for publications. Absolutely.
Excellent. So if anybody needs your email address, they can either reach out to CUAHSI or you directly. So now we have some audience questions. Both have come in through the chat and through the Q&A. One I'd like to start with is, how can we expand this initiative to the New Jersey and New York coastal regions? Or I guess more broadly, how do you expand what you've been doing in Virginia to other areas as well?
So that's a great question. And it's come up, of course, in the last week, of course, because of the impacts of Hurricane Ida. Unfortunately, I dusted off the grid that I used in 2012 and 2013 for Hurricane Sandy when the storm came through just this past week. And, some of the challenges that are involved in terms of validation is that, of course, when we've run these simulations is then, well, what do we validate? our models with. We've got, high water marks normally for these types of events. The U.S. Geological Survey has got a great field team that they'll send out and collect rapid deployment gauges along with survey these data afterwards. And of course, NOAA's water level sensors are infinitely useful every time any of these types of events come through. But usually IoT water level sensors and citizen science efforts, those usually take a lot of significant planning beforehand, as you may have seen. And so that's why we've always focused on the highest astronomical tides of the year, because we know when they're going to happen months in advance. It can mobilize a team of people to train individuals how to use these generally intuitive sea level rise apps. In this case, the app called Sea Level Rise, but there are others out there as well that help collect field data pretty effectively. I've used SoLocator and a couple of other apps that are available on iOS and Android platforms to help validate my models, which are basically just survey tools you can download on your phone. Even if you're not directly connected with these types of initiatives. But usually what I encourage individuals to do is, of course, work directly with higher education institutions that are helping collect these data, or some groups of the federal government have already received grants to do so. In New York and New Jersey, I'm trying to think specifically of who would be involved with that at the moment. And unfortunately, it's like, I know I've been involved with the Hudson River Foundation, a couple of others in the past, but I'm not sure specifically who would be a point of contact to get involved with the citizen science effort related to collecting flood data on a local scale. So I'm sorry I don't have a better answer to that question.
No worries. We have a few related questions on that topic. So related, what does volunteer management infrastructure look like? The mobile apps are clearly part of it, but what kind of staffing, training, logistics, et cetera, go into managing all of these volunteers? Are these volunteers part of a single core, or do they come together in a more ad hoc way?
So, and the answer is, short answer is mostly more of an ad hoc way, although there is some coordination involved. Early on in the presentation, I used the word tide captains, which is kind of an esoteric term for basically this hierarchical scheme of Karen Jakelish, that is the individual that usually coordinates, Chesapeake Bay and Virginia and Maryland's Clean the Bay Day through the Chesapeake Bay Foundation, is the volunteer coordinator for Catch the King these past several years. And she's been instrumental in basically building this hierarchical system that train a group of people that are usually teachers and community leaders to learn how to use the Sea Level Rise app. And then they hold training sessions within their local communities to train people that are interested in their neighborhoods, companies, or other nonprofit organizations how to use the mobile app. So ad hoc, but also with some training. And of course, in the last year, unfortunately, our participation's been down a little bit from previous years when we've been able to meet more easily in person to train people just due to COVID-19. But we led multiple virtual trainings last year and have already led 3 this year personally.
Wow. Another question from an anonymous attendee is, do you find private property owners are hesitant to document flooding on their own property?
That is a great question, mostly because every time that we collect data with Catch the King, we always make these data public. And of course, we don't know who is downloading those data. Individuals have to fill out a form, of course, to access the data resources and the GIS data layers that we're producing based on the data that we release from Catch the King every year. But yes, sometimes they're hesitant because these data do go into a database. And of course, possibly insurance companies may download these data and use them to inform the premiums that they are using for next simulations of exactly what they anticipate the relative flood risk to be. Since these points represent basically a community reported effort of actual flood extents, showing that there is flooding on your property beyond the extents that are already previously known by FEMA and their national flood hazard map, may pose some challenges in the future.
That's awesome. A few more. One is, are you familiar with the King Tide project on the West Coast?
I am. So there are several projects that when we first started evaluating. So Dave Mayfield is a former reporter for the Virginian Pilot, and he's kind of the brainchild of his is Catch the King. And so a lot of the initial research he did was focusing on the King Tide monitoring projects in Hawaii and those that are taking place on the West Coast. And of course, there is a NOAA funded program on the East Coast as well that we kind of have modeled parts of Catch the King with, just in this case, the data integration from the Sea Level Rise app, which was initially funded by Skip Stiles at Wetlands Watch as their executive director, and coded by Dave Richards and his team at Concursive there in the thank yous section of this slide. Have really been particularly instrumental in helping us collect all of those data. So when we got familiar with how these things were being done over there and the different types of crowdsourcing story maps that some of these have used and crowdsourcing web maps, that was one of the approaches we took early on. For the first couple of years, we actually had a crowdsourcing map through Esri's ArcGIS Online platform and the Sea Level Rise app. And only in the last couple of years, we switched almost exclusively to using the Sea Level Rise app only. And that's mostly because the data populate the map in real time with that data source.
We actually have a few logistical technical questions about your models. One is the forecasting stochastic or a spatial differential equation, or both?
So in this case, it is more of a spatial differential equation based on the, so we approach this in two different ways. For the king tide flooding, in this case, the way that we know months in advance what the maximum flood extent will look like is more or less heuristically based on what we project the water levels to be. When we're projecting things for like hurricanes and wind-driven events, we're using, of course, our hydrodynamic models that are forced with winds and pressure fields. So the information that we release months in advance to show our citizen scientists where we anticipate the maximum flood extents to be is mostly based on GIS static map layers based on where we've seen flooding take place in the past and the anticipated flood thresholds based on the harmonic analyses that we use to drive the tidal curves that we expect at each of the different sensors throughout coastal Virginia. And then we update that model a couple of days before the event to incorporate things like rainfall, wind effects and local weather effects that are anticipated on the day of the highest astronomical tide of the year. And naturally, in some cases, depending on wind direction, it may actually lower the water level, while in other cases, it may raise the water level based on compounding effects of rainfall. So unfortunately, the answer seemingly is confusing because it's both. GIS model far in advance, and then when we get much closer, we're using our physics-based model that's driven, of course, by wind and pressure fields and rainfall forecasts.
Well, I'm sure also if people want to know very nitty-gritty specifics of your equations, I'm sure they can reach out to you for that as well.
Absolutely. Yeah.
Okay.
Actually, it's solving the Navier-Stokes equations for our shallow water equations for our physics-based models.
Another question is, have you ever used satellite data to assess or calibrate models or to compare to crowdsourced data for how many hours does the flooding last, and is it possible to capture by satellite?
Yes. So in fact, the example that I was kind of showing for Hurricane Matthew in Virginia Beach, that was one of the things that we were kind of particularly sensitive of, is that when you get these compound flooding events, one thing that models really tend to struggle with is the relative period of how long does the water stay after these flooding events take place, mostly because you're dealing with heavily beleaguered, storm drainage systems that may be now backed up due to all of the debris that gets washed into them. And naturally, that's a sore spot for a lot of models as we're trying to consider, well, are these unimpounded systems where there's no sediment, dirt, and other things in them? And we're assuming that they're performing at 100% capacity, or are they already blocked by the last major storm event, like for example, Hurricane Matthew in 2016. It was not the first storm that took place in that same week. In fact, Tropical Storm Julia directly before that had already washed a bunch of debris into the storm drainage systems in Virginia Beach and in Norfolk less than 6 days prior to Hurricane Matthew impacting the same areas. And so one of the challenges that's involved with that is our models usually assume that there is the full 100% capacity available, and that may or may not always be the case if there's an immediately preceding storm that already has standing water in certain areas. So to answer the question, really the challenge in terms of trying to keep track of, do we validate our models for how long standing water is in certain places for the period of flooding from a temporal perspective? Yes, and that's particularly important, mostly because standing water in an area for only an hour or two is not quite as bad as standing water for days or over 24 hours. Naturally, things that are immediately impacted when water first hits them, like electrical systems, for first floor elevations of buildings, is important for us to immediately assess storm impacts and relative damage assessments. especially the impacts of waves on top of that. But for some areas, the period of flooding over longer periods of times economically also impacts areas differently than just a storm surge that lasts an hour or two. And that's oftentimes why you'll see nor'easters become a continuing problem in certain areas, because the time period that those storms last may actually trap people in certain peninsulas that now become islands when the water levels are high enough, or sometimes multiple tidal cycles, which then of course may lead to multiple days in some areas, which ultimately traps them from being able to get more food if they have to go to the grocery store, or supplies if they start to lose power.
We have a few more questions sort of on the volunteer end of the spectrum. One is, how do you guide your volunteers to ensure that they are capturing the maximum tide? And how do you ensure the data validity of volunteers collected, the volunteer collected data given error inherent in phone GPS? Is the inability to traverse private property limiting in your model validation?
So the short answer to that question is yes. It's kind of problematic in terms of minimizing error attributed to the relative GPS inaccuracy on mobile devices. One of the things that we first ran into at the Sea Level Rise app is that, basically you've got a survey crew that's going out there with 20 different survey devices or more. The first year we collected data from Catch the King in 2017. I think we identified 18 different phone models that were being used. And in some of those, there were the latest versions of the iOS and Android Google Pixel phones that were out there. And then you started seeing folks that had phones that were 2 to 3 years old with maybe an operating system that was a year or two old. And in some cases, they've made tweaks to the enhanced GPS systems on those devices that I was able to ultimately, and I'm getting in the process of publishing almost a separate paper just on the GPS accuracy alone. Because as you can kind of see in the background of this slide, there are several points here on Virginia's eastern shore where enhanced GPS cell signal from nearby towers that are used to help enhance the satellite GPS data that we have available. Of course, fewer and far between in rural areas like the Middle Peninsula and Northern Neck. Of course, further in the northern reaches of Virginia are, of course, not as populous as the dozens of cell towers that can help better triangulate individuals' positions in the cities of the southeastern portion of Virginia. So in terms of training our volunteers to collect the best data in the best places, we usually try to encourage folks that are collecting in the interest of urban flooding resiliency to target specific areas that they happen to know that there is best triangulation of their data. Most people know where cell signal is already weak when they make phone calls in rural areas. And so we've encouraged them to try and focus on areas that they know of that flood in those particular spaces first. That way they don't have a bad experience the day of when they're trying to collect data and their phone can't even get a signal for the spots they're trying to collect data. So that's why you actually see on this map much fewer data points on Virginia's eastern shore. Most people are familiar with the fact that actually a very significant amount of flooding happens on Virginia's eastern shore in terms of relative land area that is covered. But the relative accuracy on the horizontal scale of individuals that are collecting data in those spaces is unfortunately much weaker than those in the urban environments, just simply due to the fact that there are less points to triangulate data points with. The Sea Level Rise app helps triangulate data using enhanced GPS, using, of course, mobile cell towers via broadband data, but also it does incorporate data from Wi-Fi and Bluetooth as well, since many of our devices that we're using as wearable technologies are now also attempting to transmit their GPS locations. That does help use more than just the traditional enhanced GPS signal, because even when you're within Wi-Fi range of most Wi-Fi routers and modems, nowadays, a lot of those modems, just to keep accurate timekeeping, they also have a GPS device that's reporting their general location unless you manually turn it off. And so even if you're not connecting to those networks, your phone knows which Wi-Fi networks it's within range of to connect to. And as a result, that can also help, especially in urban environments where you may have 20 routers within your location's general range of your phone. The more antennae that are inside of these phone models from a hardware perspective, and on the software end, the more overlapping data that our phones can use to further triangulate our position usually ends up helping. So unfortunately, in rural areas, this doesn't help very much, but in urban environments, we have extremely accurate data.
I think we have time for one last question. So before I get to that, I would like to encourage anybody whose questions we did not have time to get to reach out to you. I'm sure that you'd be happy to continue this discussion. But our final question is first to say amazing work and impressive volunteer recruitment. But the question is, do you have any super users? And if so, what characteristics seem to make someone a super user? Is there any sector of society you think you aren't reaching or tends not to participate?
So that's a great question, because it's like basically trying to expose, what is the secret sauce of what makes certain people specifically very engaged in this particular, citizen science effort. And interestingly enough, I'm a relatively young researcher. And so, as I've been going out there and collecting data with this mobile app for years, I always run into individuals that have lived in these communities for decades. Then they're saying, oh, this storm is nothing. I remember heuristically, my experience previously, these are the big storms. It was like Hurricane Isabel in 2003. And looking back to the 90s, the last major storm events that have come through, and Northeasters in 2009. And so a lot of people will kind of describe what they remember the flood heights to be in their particular areas. And those are the people that tend to be most significantly engaged, as individuals that have lived in their community for a long time. And that's what kind of ultimately begat this project called Catch the King in the first place. Is Dave Mayfield, an environmental reporter for 23 years at that point, back in 2017, had been writing about this issue for years and reporting on it. And finally, he just said, I want to do something about it. And so, I've been trying to do something about it for years, but he was able to empower myself along with Skip Stiles to not just have ourselves and, have a small handle about, 24 people collecting data, but we're able to leverage the readership of the Virginian Pilot and the Daily Press in coastal Virginia to help get them engaged as well, not just from an educational perspective, but also to enhance the data that we were collecting to help validate our models with. And so from that perspective, our most engaged volunteers are individuals that have been dealing with this situation for a long time. Some of them have been directly engaged on local boards with their local communities. For example, we've got some volunteers that, no matter what storm event there is, they'll go out and help collect data. There's a few folks in Virginia Beach, a few folks in the city of Hampton, Newport News, Norfolk, and Portsmouth. And we know those individuals in each city that will actually go out and help collect data in their neighborhoods that will then pass that information to local planners in their community to help advise their long-term planning for their, in most places nowadays, Virginia's putting the final touches on their state's master resiliency plan, but also most communities are developing them in cities and counties as well. So we provide those information based on what's happening in their communities on the neighborhood level to advise their long-term community planning. When people know that's what their data are going towards, that's how they continue to remain engaged in these efforts. So it requires some stoking of the fire on my ends, but also others that are better on the media side, like Dave Mayfield and others, to really assist us in keeping this thing going to year 5 next year in 2022.
I think that's a great note to end on. So we're at time at 1 o'clock, but I just want to thank you again for speaking with us today. I wish you all the best with the work. This is really impressive and really important work that you're doing. So thank you again.
Absolutely. Thank you. Appreciate the opportunity to speak, and thank you for all the great questions.